The broadcast is now starting. All attendees are in listen-only mode.
Hello, everybody. Welcome to this month's Sustainable Labs Canada presentation webinar. Today we have Jacob Semanis and Justin DePaulo from SLCan Hennessy Group in the US. They're here to present the presentation you see before you, Roadmap for Designing Net Zero Labs. So we're very happy to have them on board. Just wanted, by way of introduction, to read through their bios briefly. Jacob is a registered mechanical engineer with 30 years of experience in healthcare, science and technology, and higher education project designs. Over the past 20 years, he's served in various positions, ranging from senior mechanical engineer to principal. He has a particular interest in low energy performance building design, integration of sustainable design principles, and reduction of resource consumption and complex commissioning. Justin is a licensed professional mechanical engineer and energy analyst who aspires to make continual positive impact in the fields of sustainability and engineering through energy consulting services, education, and advocacy. Justin has proven ability to deliver high-quality analysis via holistic building energy modeling to guide architectural and engineering design and optimize building performance. Justin's passion for sustainability has led him to become an active member and leader in advocacy groups such as the International Living Future Institute, Eco Districts, and USGBC. His diverse portfolio of projects spans many market sectors, including aviation, commercial office, education, healthcare, life science, institutional, R&D, manufacturing, transportation, multifamily residential, and hospitality industries. So without further ado, thank you, Justin and Jacob, for being here today, and take it away.
Okay. My name is Jacob Semanis. I'm a mechanical engineer. I am a technical lead for Western States SLCan Hennessy Group. Now, a few words on SLCan Hennessy. We are over 600 people strong. We have around 18 branches, mostly in United States. We are covering mechanical, electrical, plumbing disciplines, including, in addition to vertical transportation and low voltage. Roadmap for designing net zero labs. Actually, I wrote an article a couple of years ago, which was published by Prism, which is online architectural publication dedicated to sustainability. Fortunately enough, I had over 5,000 people throughout the world in architectural engineering community reading this article and giving me feedback. The feedback was mostly positive. Now, in this presentation, which you're going to see in a second, we are featuring quite a few photographs from a project which is a bioengineering building designed by Rubel Yadel and SLCan Hennessy, providing the supportive engineering effort. Also, in the presentation which we have present John Passananti, who is our managing principal for Western States. So, Justin, take it away.
Thank you, Jacob. Hello, everybody. My name is Justin, and if our bios weren't long enough, I will reintroduce myself as the lead of the High Performance Solutions team here at SLCan Hennessy, specifically for the Southwest region. Our team supports the engineering group as well as our architect clients on energy modeling. So SLCan has a number of projects that have pursued net zero energy or net zero ready, including some other certifications, obviously LEED, and including Living Building Challenge and WELL. A couple of net zero projects that I'll highlight really quickly include a couple in the Southwest region called Maker's Quarter Block D, which is a mixed-use complex, which has employed some innovative strategies like actuated exterior shading devices. Another project is Palomar College Operations and Maintenance Facility, which is a really fun campus building that has solar chimneys for passive natural ventilation. Both of these projects are tracking net zero energy performance as well as LEED Platinum certification, which is very exciting. We also just completed a conceptual design study on a new academic lab building at CSU San Marcos, studying the feasibility of an all-electric net zero energy lab facility. For that feasibility phase, we're looking at heat recovery chillers that can serve an in-slab radiant piping. So we'll have an all-electric and net zero as the goals, with heat recovery to serve the in-slab. So without further ado,
okay, the idea of this presentation of how do we approach a building for net zero, we can do it in 3 steps. Step 1, utilizing building configuration and planning to provide a better response to the environment. Step 2, implementation of energy saving features, options, which would be available to reduce the energy use for the total building. And step 3, the remainder of energy use of renewable systems to cover it. Definition: the net zero building is when total amount of energy which is used on annual basis is roughly equal to the amount of renewable energy created on site or somewhere else. The 2 points which I'm trying to bring in here is that we are looking at consumption on annual basis, not on any given day or month. And the second point which I would like to bring in is renewable energy somewhere else. It's not necessarily will have to be all generated on site, but it needs to be dedicated to a specific project.
so we've introduced the topic, but let me set a little context first. I'm sure that you've heard that global temperatures are rising and glaciers and Arctic sea ice are irreversibly melting, which is causing sea levels to rise continuously and threaten our coastal environments and coastal cities. Storms and droughts are getting more and more extreme and devastating. The debate is almost out on humanity's involvement in this developing crisis. Whether or not you believe you are contributing to this, it's undeniable that buildings consume a lot of energy. In the United States, buildings account for at least 40% of the energy consumption and nearly 50% of carbon emissions. So not focusing only on the bad stuff here, the good news is that public and private entities around the world are stepping up to create policy and set goals to help reduce our footprint on our planet. For instance, there are more than 10 US states, including California, that have committed to 100% renewable or clean grid within the next 20 or 30 years. The UC, which is the University of California school system, went a step further. They actually elected to be 100% renewable by 2025, so only a few years left for them to figure that out. There'll be on-site renewable as well as green power purchasing, and that'll be for all of their campuses. The California Energy Commission has adopted net zero energy goals, which is pretty fantastic. They're pushing net zero for residential by 2020, so only in a few months. Our next code iteration that will be released in January 1st of this coming year will be the biggest driver for net zero for residential, and then the same will be for commercial by 2030. We're also seeing municipalities push policy like Santa Monica, creating their own solar requirements ahead of their state's policies. So we're excited for the good news. Okay, so how do we do it? You know, laboratories are very energy intensive, but all buildings consume energy, so every project can be approached in the same way. And I like to borrow the 3 R's from the recycling, which is, of course, reduce, reuse, recycle. And in use that as a mantra for approaching any project in the built environment, which would be converted to reduce, reuse, and renewable. And the reason why I like to use that mantra, and the reason it stems back to the explanation that Jacob provided already, which is the step-by-step process and the order of those steps are really important. First, we want to reduce the inherent energy intensity of the building through good design practices, both architectural and through engineering, passive design strategies, and efficient active strategies. Next, we reuse as much of the energy that has been consumed as possible. So heat recovery strategies, whether it's at the chiller plant or in the exhaust waste stream. And then, of course, when we are able to reduce our energy use intensity, our EUI of the building as much as possible, then the renewable energy aspect becomes much more feasible. I have a little diagram, the next few slides here, which describes that process in using the size of the PV array to scare you into energy efficiency. So the image we're looking at is actually a cartoon of the headquarters of the International Living Future Institute. They are the organization that has created and manages the Living Building Challenge, which is the world's greenest, or the most stringent green building certification. So this project, this is a real building. It's already occupied, about 85 or 90% occupied. It's in Seattle, Washington. Some of you may have actually toured this project. It's a beautiful building. If this project were designed to meet the national average EUI, the national average energy use intensity of about 72 for an office building, the size of the PV array would be absolutely absurd, as you can see on the screen. If we take it a step down and we look at just meeting and complying with the Seattle Energy Code with an EUI of about 51, sure, the PV array shrinks a little bit, but it's still massive and would be too expensive and unrealistic, and structure couldn't handle it. We're also shading our neighbors' rooftops and preventing them from producing their own on-site renewable energy, which we have to be good neighbors. So we have to keep focusing on renewable energy and energy efficiency. We drive that further and we look at an EUI of 32 following LEED Platinum, which in this assumption we're assuming 18 energy and atmosphere points. Still reasonably, smaller than before, but not as good as we can get. We shrink that roof as much as we can get to about an EUI of 16, applying all the energy efficiency measures we can, and then the PV array that offsets that energy consumption actually fits on the roof. And this building is operating at a 13 EUI. The 16 was predicted, its actual is 13, and people are jumping up and down as if it were the greenest building in the world, and it's pretty much closest to that. So, all right, well, that covers the introduction. So we are ready to move into how we apply that step-by-step process to laboratories. First, starting with building configuration and planning. So we always want to start from the outside and make our way in. So orientation and massing is where we start. They have a substantial impact on building performance and can impact upwards of 15 to 20% on their cooling and heating loads. Typically, we want to orient buildings along a east-west axis, but this idea only works really if we have adequate solar control on the south, east, and west facades. Self-shading must be considered when studying massing options as well. And of course, it's easiest and cheapest to include certain architectural design elements at this stage, such as courtyards or light wells and atria, all of which play a role in energy performance, daylight harvesting potential, and occupant happiness and productivity. Looking specifically at the programming for buildings, I think we've all probably seen wet labs placed in basements or away from windows. I know that at the University of Maryland, which is my alma mater, all of the wet labs were underground and without windows. Excuse me. But we learned that it's actually best to locate wet labs along the south facade, because wet labs and southern exposed zones require the highest airflow rates, so it makes the most sense. Another programming lesson learned is that it's also good practice to isolate HVAC systems and dry labs, for dry labs and support spaces from wet labs, to separate the HVAC that serves dry and wet, to reduce the burden of the wet labs on the rest of the building. Okay, moving into external shading. It's the next passive design strategy that we must address after looking at orientation and massing. focusing on having adequate solar control on the south, east, and west facades. The intent here is to maximize daylight harvesting with diffuse light and minimize direct solar gain. On the south, this means deep horizontal overhangs. On the east and west, we want to look at vertical fins to block morning and evening low-angle sun. Of course, this is true for the northern hemisphere. These shading elements could be solid or perforated. A lot of different architectural features can be applied here. An innovative strategy to deal with varying solar angles is to utilize actuated shades that move with the position of the sun. The net zero project I mentioned at the beginning of this presentation, the maker's Quarter Block D, actually has actuated sides, pretty cool. My favorite shading device is actually a deciduous tree. You get the shading benefit during the summer months. When the leaves fall off in the winter, you take advantage of the direct solar gain to help reduce heating loads. Okay, next step on the passive facade journey is the facade system itself. There are obviously many options, and these decisions are often made by the owner and architect because, well, you know, construction types have a huge cost and aesthetic implications, so we leave it to those who should make those decisions. But us analyst engineers are always willing to provide recommendations and run studies to test design options. The image on the slide that you're looking at is of a double skin facade, which is fantastic, but very costly, obviously. Method of super insulating a building by creating a large air insulation layer between facade elements. The heat gain in the cavity can be exhausted or used for space heating. This strategy is more effective in extreme climates. Doesn't really work too well in moderate climates like where we are in California. But in California and in similar climate zones where we have high diurnal temperature swings, a very simple yet effective construction assembly is one that provides significant thermal mass, like a CMU wall, precast concrete, or rammed earth. I'm sure you know this, but thermal mass is like a battery, so we are able to shed thermal load during the day of absorbing heat and then release it at night. There's also manufactured products that can be included as a layer in a wall or roof assembly that provide the equivalent of 6 to 8 inches of concrete in just a half inch of material. Okay, now let's talk about glazing. Now, you know, glazing can be a sensitive subject as we start looking at window to wall ratio and reflective tints. Jacob and I were just talking about how energy analysts like myself typically try to persuade architects to reduce the window to wall ratio as much as possible, which is definitely true. But he brought up a good point that as engineers, we don't want to be at odds with architects. We want to support them and make their design functional and efficient. So I'm trying to learn from this insight. Instead of fighting for more opaque areas, we should be helping to find glazing products that meet the desired aesthetic as well as the desired energy performance. Because glazing technologies are continuing to improve, and we can find really low U values with thermally broken framing systems, vacuum insulated panels, argon-filled IGUs, and we can drive down the solar heat gain coefficient with a clear glass rather than that stereotypical and hated blue-green tints that we're all used to on high-performance glazing. But now we can look at more clear units with low solar heat gain coefficient. So keeping on the subject of high-efficiency glazing, whether we're going with a curtain wall assembly or window wall or punched walls, there's some really interesting options available that will help reduce the external gains while letting diffuse light in for daylight harvesting. Of course, there's double and triple pane assemblies for the U value, but there's also really cool frit patterns that we can apply that help with solar control. Some of the most interesting glazing on the market is the electrochromic and thermochromic glazing, which offer dynamic response to external gains. And let's not forget about operable windows, because natural ventilation is obviously very important, and in climates, most climate zones can support operable windows, and some are better than others. Of course, we want to interlock operable windows with the HVAC to prevent conditioned air from escaping to the outdoors. Last on my list to talk about is daylighting. I've been focusing mostly on the thermal performance of the exterior windows, but there is also the obvious benefit of daylight harvesting and the effect that natural daylight has on occupant happiness. There are several ways that natural daylight can be introduced into the interior of a building. besides through vertical glazing, of course. Light wells like atria, and the atria shown in the image on the screen, create a light and airy space, which is perfect for entryways and lobbies. Light shelves can be used to increase daylight penetration, and reflective interior surfaces and finishes help to extend daylight further. Besides the benefit of reduced artificial lighting, there is also the psychological effects of natural daylight that must be considered. And I don't think we need science to tell us that there is a direct correlation between natural daylight and our occupant productivity. In fact, there's a rule of thumb that you've probably heard of, that for the total cost of ownership of the building, capital costs only come to about 1%, operational costs over the life cycle come to about 9% of costs, and then the remaining 90% is associated with employee expenses like salaries and benefits. So helping to improve occupant satisfaction and productivity makes a huge difference to an owner's bottom line.
All right, so the next step in the design of net zero projects will going to be related to energy use and sustainable energy systems, which will going to allow us to reduce the energy being utilized or used by the building. In this particular step number 2, my intent was not to cover everything possible which can be implemented. It was rather to go through some of the major options and sustainable approaches which can be used in laboratory building. So first of all, I like to start with low velocity fume hoods. In this particular approach, California stands out in rigid requirements of 100 feet per minute so far, but other parts of United States and obviously abroad, we can use a low velocity fume hoods, which will gonna reduce the velocity through the fume hood opening from 100 to 60 feet per minute, which automatically will gonna bring you a reduction in energy use by 40%, because the air which is being exhausted from the fume hood will gonna be released outside of the building. Now it needs to be replenished, and now we're gonna have some heating and cooling which will need to be attributed to this air being brought inside of the building. And the important thing is that in laboratory buildings, 75% of energy consumed is consumed by mechanical systems, and this is critical. Now, in addition to that, we can have other strategies like hood sash closure that can reduce the energy as well. Now, if we're going to be looking at other approaches which are being implemented in Europe or in Asia, there are some fume hoods which is considered operationally safe with 40 feet per minute, which means a 60% reduction. In the United States, specifically in California, we have another thing which is implemented and getting a momentum is fume hoods, which are going to have filtration inside, and therefore they will going to be 100% recirculated and no exhaust will going to be needed. We have some laboratories which are currently fitted with these fume hoods, and they are being successful in their operation. Next is radiant hydronic heating and cooling, and you can see my favorite picture. This is basically from the project which is UCSB, which I mentioned before, which actually was Platinum LEED project. Now, for this particular approach, we can use hydronic heating and cooling, which can be built into the structural elements like floors, can be built in walls or ceilings, whereby the heating and cooling will going to be slowly released with a gap of several hours into the space, provide very comfortable temperature and setting within the space. It is very energy efficient system because your heating and cooling is being delivered through the water rather than through the 100% of it being delivered through the air. It's a lot more efficient to deliver it with the water. In addition to that, if you could see in the ceiling, there is a panel which is chilled beam system. And as you know, there are two options available. One is passive, one is active. The difference is that active system will going to provide you additional air which will going to be distributed in the space, which will going to be required because to compensate exhaust of the fume hoods and to provide ventilation air required in the space. Energy efficient, low noise, provides additional comfort, and actually would be an unbeatable system to use. Let's look at demand ventilation. And basically, we have two concepts which I would like to go over here. One of them is traditional, when we have a thermostat in the space, and we will gonna be delivering amount of air based on the requirements and position which will gonna be subject to the thermostat setting. The second option, which is important to bring up here, which specifically would be working very well, would be when internal air sampling will going to be provided for to verify the amount of chemical components which will going to be in the airstream of each specific area. And based on that, the amount of air can be delivered more or less, providing a dilution capability and increase exhaust capability from laboratory space. Now, chemical compound, it can be VOC compound, it can be particle counter attached to this system. And for instance, if you are in a situation when you are at night, when no people are present, you can slow down the system and bring it to as low as 4 air changes per hour or even lower. In some instances, you can go up to 2 air changes per hour and provide substantial savings from the ventilation requirement. Displacement ventilation. One can say that displacement ventilation cannot be used in laboratory. It's given because you always have a danger that you will going to have a spill of chemicals, and chemicals will going to get into underfloor situation. So floor outlets in laboratory environment will not going to be acceptable. However, you can use them on a low wall and it will going to be as successful. Besides laboratories, each building will going to have public areas, we're going to have offices, some buildings will going to have auditorium. We have plenty of spaces where displacement ventilation can be used. Energy saving up to 50%, very comfortable environment, very with a very reduced noise. You know, one of the issues in mechanical systems will going to be noise generated by mechanical system. Displacement ventilation will going to be able to provide you a superb comfort. Natural ventilation. Installing operable window in laboratories in the United States is not the preferred methodology for natural ventilation. I know cases when in Europe, I know some cases in Asia where natural ventilation is being used in labs. Our preference in the United States is to keep the environment with reduced particle count or some other gases which may enter an effect of what's being done in laboratory environment. However, again, we have plenty of spaces within laboratory projects where a natural ventilation can be used successfully. Office area, public area, and this will gonna provide you very energy efficient solution and very pleasant environment for the occupants. In this picture which you see here, there are some options of designing natural ventilation. This particular space is office space, and in addition to that, we can have an option of fan assist strategies, which can be on top of that thermostatically controlled as well. Mixed mode air conditioning ventilation is getting superb implementation in California where we are. But not only in California, you can see back east projects which are being designed with this concept in mind. This is basically a hybrid solution whereby you are going to have air conditioning which can be utilized at a given times and period of the year, which are going to be coupled with some of the exterior which can be openable. And in this case, when it is openable, then air conditioning system will going to be just, let me simply say, in off position. So a hybrid now, which is very easily to control. A preferred solution in springs and summer throughout the country. Improves air quality, reduce carbon emission, and provide you options which are which we're going to have inherited adaptability. Occupancy and daylight sensors. Very important tool in increased energy efficiency. Very simple to install devices, adjusting lighting levels within the space, amount of lighting entering into the space from exterior can be easily implemented in building controls and very inherent in energy efficiency and sustainability, which are going to be provided for the building itself. Sensors, we are getting continuously new sensors which are being technologically more advanced, which can provide passive infrared or ultrasonic options for the controls. In addition to that, we are getting to the times when other control systems are being engaged for the building controls, which easily we're going to be able to implement additional daylight and occupancy solutions. Heat recovery options. California is the place when not all heat recovery options can be successfully utilized because we call ourselves as economizer country. Many parts of California would have a very mild climate, which are going to be able to provide the best solution for economizer when you're going to be able to exchange 100% of the air from outdoor, bringing it indoor. However, we do have certain areas where we have over 100 degrees in Fahrenheit in summer and below 40 degrees of Fahrenheit in winter, where heat recovery options were going to be very successful. One of them was going to be runaround coil. Runaround coil back east in the United States can give you a great success with 1 to 2 per year payback. Average efficiency is about 50%. You basically have 2 coils. One of them is installed in exhaust airstream, and a second one will going to be installed in outside air, which will going to be entering the building. And heat transfer will going to be through the fluid between the coils. Very easy. And as I said, in some areas you can get payback in 1 to 2 years. If you're going to be looking at coastal areas of California, this basically will going to give you a payback of about 10 to 12 years. So depends on the area, it can be successfully used. Another option which I would like to mention in here is a heat wheel, which will going to consist of circular matrix, which will going to be rotating within 2 airstreams. Again, one of them will going to be exhaust, which we have plenty of in laboratory projects, and the second one will going to be located in the airstream, which we're going to be bringing inside the building from outdoors. The implication of this strategy will going to be that 2 to 3% of the air which is being exhausted can be interfaced between the 2 airstreams. So it means that as a designer, if you are looking into these options, you need to consider, and the most, let's say, obnoxious areas of the streams need to be exhausted by dedicated systems. So can be used, but needs to be used carefully. Efficiency is approximately 85%, which is by far better than runaround coil. Additional strategies. This is the slide which I put in, counting on reducing the amount of slides which will going to be a part of this presentation. Just thought to mention, one of them will going to be digital control systems, which are going to be able to provide you resets, night setbacks, and we're going to be able to provide you with measuring capabilities. The second item which I would like to mention is here is building commissioning, that after the project will going to be done, we'll be able to commission the building and fine-tune it to the best performance, that whatever you as designer had in your mind for the building to perform, you actually would be able to prove and fine-tune it for the building to support your ideas. And the final step for the net zero project design will going to be use of renewable systems. There are several options which can be used for renewable effort. And they can be successfully used in building. So I mentioned 5 of them: geothermal, sun, wind, tides, waves, you name it. However, the most frequent use will gonna be geothermal, sun, and wind. There is another idea which basically we mentioned somewhere before in the presentation, which was partnering with the community to develop district renewable systems. And we need to say that this is a winning strategy. We have several laboratory projects which are net zero based exactly on this strategy. As we mentioned before, the important thing is that this green power would be dedicated to a specific project, that we would not end up with a situation when the same green power being attributed to several net zero buildings. That is very important strategy to mention in here. Geothermal. Geothermal energy is a thermal energy generated and stored by the earth. Today we have a lot more available options than we had just a few years before. The strategies and know-how which were generated to oil and gas industry allows us to perform much bigger and better with geothermal. We are able to go inside the earth for miles deep, or for the same token, miles in horizontal, to look for the best areas which we can use as heat exchangers for heat of reversion, or heat exchangers or ground-coupled heat pumps. Both of these strategies are used quite often. In addition, we do have some areas where we are able to connect to the streams of heat in underground position, which we can use for absorption refrigeration or even for direct heating as well. Even that the heating medium can be like 100 degrees, that may be good enough to support the heating cycle. In some areas where we have a steady cold streams available, we can use it instead of chilled system altogether. Solar system. If you are in downtown Los Angeles and if you're gonna look at the buildings surrounding you, you're gonna see that a lot of buildings will gonna have solar panels. When we are talking about solar systems, solar power, we are talking about solar farms, whereby we're gonna have a lot of solar panels which are gonna be able to provide us solar energy. Now, for renewable systems in California, this is a #1 solution, which a lot of buildings or even municipalities, UC campuses are moving to. And that will gonna be a choice for us down here for the solution. Now, we also may have federal or state incentive, which are gonna allow you a lot better and faster payback for this system installation. Wind power system. And when we are talking about wind turbine, we are not talking about a single one turbine. We are talking about a farm which will gonna consist of multiple wind turbines. And last few years we are going through development, more and more efficient systems which are going to be able less and less affect the environment, and that is very important item. Now, in the United States, it is used, but not that much. But there are some countries where most of the renewable systems is being derived from wind power. And one of these countries would be Germany, where 70% is derived from wind power, which can be installed not only on ground, but we see some installation going deeper in ocean where farms are being installed and operational successfully.
Okay, thank you, Jacob. And just to quickly wrap up our presentation on the roadmap for net zero energy labs. Again, labs are very important building type to focus on considering their energy intensity, the process loads, and high air exchange rates that are necessary for ventilation. So we are very interested in the development of net zero labs and the processes that we presented today, and we hope that you enjoyed. So we would like to open the floor for questions, and thank you so much for listening to us today.
Thanks, Justin, and thanks, Jacob. There are some questions that have been submitted already, and for those people who are in attendance, please feel free to submit your questions in writing down below in the questions dialog box. I'll relay the first couple questions. One of the comments that you made early on in the presentation, Justin, was around the feasibility of putting lab spaces on the south face of the building rather than the north face of the building. And the question here was, does this solution or strategy change depending on the geographic area? For instance, cold versus cool versus warm or hot climates?
Basically, let me just start on responding to this question. Obviously, the performance of the building will gonna be depending on the building configuration. Besides that, it will gonna be depending on, as you mentioned, climate. In one climate, one strategy may be a lot more preferred. In another climate, it will gonna be less preferred. Laboratory buildings, the biggest load will gonna occur in laboratory space itself, when we will gonna have multiple fume hoods, which will gonna require exhaust, which will gonna require increased air changes. And what Justin was saying is that was specifically the space which we are referring to. It wouldn't be exactly a laboratory with very low intense, the one which we're gonna drive the solution which Justin forwarded. In this particular case, a high air change within the laboratory, which will gonna be coupled with increased air change on south orientation, sort of coupling high and high, will gonna provide us some saving in strategies. I hope I'm answered.
No, that's helpful. Thank you, Jacob. The next one, regarding runaround coils, have you ever used a heat pump between the two coils to boost heat recovery temperatures?
Yes, this is, myself I didn't, but I've seen systems which are using this strategy and using it successfully. Again, as I was mentioning before, we are not trying to cover all and each available solution. What we were trying to do is just to cover some of the solutions, which gives you a good feeling and idea of what we are trying to do and how to achieve it.
Fair enough. The next question here from one of our listeners was, have you had any success in retrofitting existing labs specifically to lower emissions or CO2 emissions?
You see, let me try to answer this question. We have a lot of campuses in Los Angeles which have very old laboratories, which were designed perhaps 50 years ago. From the same token, we have some laboratories which were designed 50, 70 years ago, and they were implementing the superb strategies. One of them, which I would like to mention, is SLC Institute, which was designed, I believe, something like 50, 70 years ago. It has interstitial space. It had manifold exhaust system. It's just wonderful the way it was designed way before. Now, besides that, we have we have several campuses which has multiple buildings. I will not going to mention them, which has older and obsolete systems. I know that we were coming in, we were converting this system, implementing latest strategies, providing the payback, excellent payback to the clients. And today, when energy becomes a very important issue which requires a lot of proactive solutions, yes, we can do it. And yes, we are doing it.
Okay. The next question is about equipment use and planning for unknowns. The question here speaks to the fact that during design, sometimes the equipment use in labs isn't necessarily known. So the question here is, how do you consider equipment use in labs when you're calculating for net zero energy? And how do you approach a project when the equipment load is not known specifically during design, or maybe is subject to change?
You know, this is a very interesting question. And basically what we do is we approach it in a way by saying that MEP engineer is not the one who designs the building. We are designing the building as a team, which will gonna include equipment planners, architects, and the owner. All of us together will gonna make a decision which will gonna be able to reflect the needs of the building going in the future. And there are two ways of how to deal with that from mechanical perspective. First of all, the most efficient what we have is water. Delivery of cold or heat water is very energy efficient, very easy to implement, and very easy to account for future. And then if the mechanical systems will gonna be able to implement a little bit of additional air quantities for supply and exhaust, which is easily achieved, which will not gonna be a running load, but again, something to look at the future requirements for the building. And again, we don't do it in isolation. We approach it as a team. We are looking at strategies where the client would like to see the buildings will gonna go, how it will gonna be used, and then what would be the impact to MEP system to accommodate the future use.
And then to piggyback up on what Jacob is saying, which is absolutely true, thinking about how it is a team approach and we have to rely on our teammates, just using my last experience on the feasibility study I mentioned for the CSU San Marcos Net Zero Lab. Again, it was a feasibility study, but we had all of our teammates on board early, and one of our teammates was a lab consultant, and so they work on multiple lab projects. They understand what equipment is typically specified, whether it's air compressors or electric equipment or what have you. So we are able to try to summarize that information in the energy model. And as I'm sure you all are aware, when we're looking at net zero energy, it's not about our relative energy comparison to a code baseline or an ASHRAE baseline, as if we were doing LEED or Title 24 energy code compliance. We're thinking about our absolute energy consumption. And the assumptions that go into the energy modeling are very important, especially when we're using renewable energy to offset. So we have to be very careful when it comes to those assumptions, and using the information from our lab consultants often is the first approach.
Okay, thank you for that. That's helpful. Related to a question that I had, which is, whether there are specific lab types that are more amenable to a net zero target than others, and where that comes from is, understanding the diversity of fume hood use and other specialty exhaust equipment uses in certain lab types, for instance, analytical chemistry labs, where the number of square foot, fume hoods per square foot can be quite high as compared to, a low level containment microbiology lab where there's very little fume hood use comparatively. So just kind of curious if you have worked on projects where there's a net zero target, but a relatively high equipment use.
Yeah, let me answer this question. Any laboratory can be successfully designed to achieve net zero result, given that chemical labs will gonna be much more intense. It's given. But the strategy of net zero needs to be decided right at the conceptual stages of the project. And then it needs to be implemented on a step-by-step basis from day one of conceptual design, and then you are going to be able to achieve the desired results. I've done chemical labs or components where we have intense chemical labs. I know exactly how intense it is. And obviously, in some cases, it's much easier to deal with that. In some cases, it's a lot more harder, but we can do it.
Great, thank you for that. That's a great answer. The next question here is, how many renovation projects has your team completed to increase lab energy efficiency? And related to that, what were the main features that you incorporated, for instance, manifolded exhaust, heat recovery, and low flow fume hoods to achieve the improvements, and what was the highest payback calculation achieved?
Well, I basically was involved in several projects, mostly in campuses in Los Angeles. And we were implementing exactly what you said, manifolded systems. This is number one, because 40, 50 years ago, the systems were designed with individual fans, exhausting individual fume hoods. So manifolding is given. In reality, it depends how the system, yeah, and in addition to that, all the features which you mentioned would be implemented, and heat recovery and so on. There is so many options which can be done. Now, the payback, what I've seen the best payback was 1.5 years. Again, it will gonna depend on the configuration of the building. It will gonna depend on availability of the system to accept the features which will gonna provide you the best benefit. And again, sampling of the air from chemical compounds and VOCs, that would be also an additional, as a cherry on top thing, and the payback is there. I would suggest that if there is a situation with existing labs which can be best solution implemented for the best energy payback, whether it is not zero or not zero, just to implement the solutions, to reduce the energy, to improve it, we need to do it, because it will going to improve not only energy, it will going to improve the safety of the occupant who will going to be working in these buildings.
Excellent. Thanks, Jacob and Justin. We've reached the top of the hour now, and so I just, want to stop and say thank you for this presentation. I think that you've positioned a three major step process that's similar to, in some ways, to the idea of no technology, low technology, and high technology in a way. And it's very interesting to see that you've emphasized the idea of looking at building orientation and holistic kind of macro moves, and then moving into the more selective use of micro moves and specific technologies to implement a net zero strategy, all based on kind of an integrated solution with the rest of the design team. So it's a great presentation. I just wanted to thank both of you for your time and for presenting to us today.
Okay, thank you so much for giving us opportunity.
Thank you all. Great to speak with all of you.
All right. Thank you very much. And for those of you on the line, if you have additional questions, feel free to take note of Jacob's contact information here, and you can reach him offline. Thank you, Justin and Jacob. Have a great day.
Thank you.
Thanks all.